In the modern blast furnaces, coke is no longer just a fuel. It's our most expensive structural asset. To optimize our cost, we must master the auxiliary injection process. You see here a cross-sectional diagram of the tear zone where hot air and pulverized coal meet at 1200 degrees centigrade. Note the core equation RR, which stands for the replacement ratio, which is equal to delta K divided by S. By the end of this session, you will gain three specific deliverables. First, a fundamental mastery of the thermodynamic driver of the replacement ratio. Second, a diagnostic framework to evaluate different injectants. And third, the operational logic for protecting the furnace sweet spot at high injection rate. So this is not just about a chemistry, it is about a diagnostic framework for iron making optimization that directly dictate your plant's bottom line. So to understand the how, we must first understand the why, the fundamental role coke plays inside the furnace. And this is one of the most important fundamental that to be shared. So mm, this visual depicts the furnace as held up by three massive pillars, and we repeatedly come across all these information and knowledge through the books, through the basic, that thermal, chemical, and mechanical requirements are prime important uh, things. The first two, thermal heat for melting, chemical agent for reduction, are replaceable through auxiliary agent. However, the third pillar, the mechanical role, is irreplaceable, and that is the reason in any context, either hydrogen injection or any fuel injection, we need to stick to this basic. So coke is the only material that remains solid in the lower furnace to ensure gas permeability and liquid drainage. And these all result in uh, that because we are this responsible for 95% of the primary metal production and the bulk of steel CO2 footprint. We have an injection mandate. We substitute as much as thermal and chemical coke as possible, but we must never compromise that third pillar of structural integrity. So this substitution is defined by a single metric that we call the replacement ratio. Now coming to our next slide, which is on defining replacement ratio, and look at this balance scale. On the left we have delta K, the coke saved. On the right, S, the injectant agent. So RR is the ultimate metric of efficiency, weighing the heat and reductant liberated by preheated coke against that liberated by the cold injection fuel. So note the distinction between actual RR at constant parameter and corrected RR, which adjust for shift in hot metal silicon, blast temperature and moisture. So without the corrected RR, you are comparing apples to orange. So understanding this equilibrium is the only way to know if your injection strategy is actually saving you money or just shifting the energy balance. So while the basic formula is simple, the underlying mathematics of substitution involve three distinct buckets, and the in this slide we are going to talk about the mathematics of substitution. So here is the expanded thermodynamic equation. It looks complex, but look at the three orange and blue bucket at the bottom. Bucket 1 is fuel quality, carbon and hydrogen are your energy source as it is shown in the bucket 1. As for the bucket 2 is concerned, bucket 2 is the gas utilization. This is the proportion of CO and hydrogen, that is carbon monoxide and hydrogen, that actually reduces ore before exiting the top. And Bucket 3 is the system loss. So because error depends on top gas utilization, the exact same coal will yield a different replacement ratio in two different furnaces. So it's not just a static property of the coal, it's an output of your furnace specific efficiency also. So of all the factors in the bucket 1, the most dominant driver is the carbon content of your coal, as we all know also. So coming to the material driver, in this slide, the carbon to replacement ratio curve that we need understanding. So follow this bright teal line on the graph. This is the carbon trend. You will notice an aggressive ascent where the theoretical RR increases strictly with the dry ash free carbon content. However, look at the plateau around 91% carbon. So beyond this point, you hit diminishing returns. We also see the volatile trade-off. The high volatile coals inject more hydrogen, which is great for chemical reduction, but drag down the overall mass to mass replacement ratio because they provide less thermal output than high carbon coals. And it is obvious also that as more VM will be there, so available carbon will decrease. So choosing a coal is not about finding the highest carbon, it's about finding where your furnace can best utilize the carbon hydrogen balance. But as we chase carbon, we must avoid the two primary material parasites, the moisture and the ash. And the very next slide is sharing on those aspects. So these are called as a material limiters, and these both component again I refer as the moisture and ash. So here we see two visual penalty, a blue water drop representing the moisture penalty and a jagged grey rock representing the ash penalty. So moisture is a thermal drain. It undergoes an endothermic reaction with carbon that consume heat. Now, talking about the rule of thumb, you need roughly good amount of substitution of coal just to replace the thermal loss of moisture. Now, coming to the ash penalty, as is ash require extra flux to melt, increasing slag volume and viscosity. So impurities are the parasitic drain on the race with thermodynamics. So high ash coal replaces significantly less coke because its energy is consumed simply melting its own waste. So to understand how these material react, we have to look inside the 2000 degree centigrade environment of the raceway, which is all about our this slide about the microdynamics, the carbon oblique hydrogen pathway. So look at this high speed schematic of the injection line. Substitution is a two-phase process. Pathway A is the volatile matter. These reducing gases like hydrogen and carbon monoxide flashes off immediately as it is shown in the slide. And this immediately promote the indirect reduction kinetically better than carbon monoxide alone, this hydrogen. So pathway B is the fixed carbon or the thermal car. These forms a porous skeleton that combustion slowly to provide the intense localized heat needed for melting. So all gives us a result, and that we are going to interpret that if the car doesn't burn completely, it exits the raceway and clog your dead man. And successfully injection requires a balance between the fast gas and the slow burning thermal skeleton. So these dynamics vary widely across the different material, which we can compare using our diagnostic matrix. And our next slide, which is about the injected diagnostic matrix. This table summarizes our option. Natural gas offers the highest RR at 1.1 1 to 1.2, providing maximum chemical reduction but requiring massive raft compensation. Heavy oil is a historically excellent balance of thermal and chemical role. Low VM coal gives you a maximum mass replacement, while biomass oblique charcoal is our CO2 neutral future, though it's highly sensitive to moisture control. So, so what? So there is no perfect injectant. Your choice depends on whether your furnace is limited by gas permeability, heat, or carbon requirement, and overall the economics too. Money matters is always important. So regardless of the material, every injection strategy must manage the gatekeeper of the process, the raft. And our next slide, which is on those operational drivers managing raft. So you see a thermometer here with a blue arrow representing the cooling effect of the injection. So recipe adiabatic flame temperature or raft is the gatekeeper, because injectants are at ambient temperature and decompose endothermically. They drop the raft tremendously. If it falls below the critical threshold, typically 1800 and 2000, melting ceases and metal quality degrade. We must use compensating measure like oxygen or blast heat to push that temperature back into the orange zone. And this result in a compensation and with cost. So the raft is your thermal anchor. You can only inject as much as you can thermally compensate for. So this leads to the raceway operating window, where we balance these competing forces. And our next slide is on those important information. The raceway operating window. This graph is the map of stability. The white central zone is the sweet spot. You must into the red zone at the top. Your oxygen enrichment has outpaced your injection and you would not have enough gas to preheat the body. So if you fall into a blue zone at the bottom, your injection has outpaced your oxygen. The flame plummets and the raceway collapse. High productivity, if we talk about 10,000 to 12,000 ton per day, can only exist in that narrow white corridor. So to stay there, you must master the control panel of operational lever. So let's look at exactly how we manipulate those levers to protect the replacement ratio, and which is about our next slide, that is about the control panel operational levers. So here are your three primary levers. Lever 1 is the oxygen enrichment. Adding 1% oxygen boosts the flame by roughly 45 to 50. Lever 2 is the blast temperature. Every 100 degree add about 60 to almost 50 to 60 degrees centigrade to the flame. Lever 3 is the blast moisture, which act as a coolant, and these levers are mathematically linked. Strategic note says that oxygen uh, doesn't increase productivity on its own. It allows you to burn more reducing agent per unit of time without choking gas permeability. So you will put these levers to protect replacement ratio when you push the injection rate. But even with a perfect heat, we eventually hit a physical ceiling, the aerodynamics of the furnace, and which is going to be one of the most important aspects while increasing our injection level. So our next slide which discuss about the physical limiters, that is aerodynamics and permeability. So these are the two pillars. So look at this bird nest icon around the dead man. This is the flooding threshold. Even with the perfect combustion, you cannot convert 100% of high PCI rate within the raceway. Unburnt car and coke fines exit the raceway and create a clogging effect that we have also discussed in our earlier presentation. So this decreases the void fraction of the coke bed and increases slag viscosity drastically. And the result, the maximum injection rate is ultimately dictated not by the thermal balance but by the aerodynamics. So if you can breathe, you cannot melt. To overcome this, modern operators use a dynamic equilibrium strategy. And our next slide is one of the dynamic equilibrium synthesis. So this graph shows the paradox of high rank coal. Low VM coal offers absolute highest theoretical RR, but it burns slowly and can choke the furnace. High VM has a lower replacement ratio, but rapidly and cleanly. The modern standard is a carefully calibrated blend. So you use LVC for high replacement and HVC to maintain combustibility and gas flow. So what is the solution? So maximizing replacement ratio is a systematic equilibrium. The best coal on the paper is rarely the best operational choice in isolation. And we must remember that changing the furnace injection doesn't just stay inside the furnace, it ripples through the entire plant. So coming to our next slide, which is on the system-wide cascades about the macro energy impact. So follow these blue and orange arrows across the integrated steelwork. Altering the injection changes your energy balance. So pushing high VM coal might lower your furnace replacement ratio, but it puts more hydrogen into your top gas. So this richer blast furnace gas is then exported to your power station to generate more electricity. So optimization is plant specific. The best injection strategy depends entirely on whether your local costs are higher for power, natural gas or coking. So let's distill everything into our three strategic takeaways, and those are shared in this slide, and which is on the thermal crucible, that is the strategic takeaways. So we wrap up with three rules for the modern superintendent or foreman or manager. So optimize for the system, not just the metric. A coal that burns flawlessly at 200 kg per ton hot metal save more total coke than a high replacement ratio coal that choked the furnace at 130 kg. The second is every kilogram of injectant is a thermal drain. You must ruthlessly protect your flame. And third is your burden quality dictates your injection ceiling. So better coke allows the furnace to ingest more unburned char. So the replacement ratio is not a fixed number, it's an engineered outcome. So master the window and you master the cost of the iron.